was by one of the participants of the discussion, Mohammed, who, from his question, you may guess that he's interested in chemical reactions which have well-defined equilibrium for reactant and well-defined equilibrium in product. So he will continue to look at the simultaneous participation of nuclear and electronic degrees of freedom, and he will contribute his effort towards nanoscience to a race of silicon quantum dots. Okay, floor is yours.
Good afternoon. Welcome everyone to my talk. So in my talk, I'm going to discuss about the Marcus theory and how can we implement this Marcus theory to describe the electron transfer in the PN doped silicon quantum dots. So first, let's start with a typical chemical reaction. If the reactant produces this example of a redox reaction, the reactant by the electron transfer is produce a product. So in this reaction, we can describe by the potential energy graph, energy graphs in the air. This is one of the example of endothermic reaction. If this is the energy of the reactant, and by the reorganization, they produce the product. So the energy of difference of this product and reactant is known as enthalpy changes, but the path is going through that way is going through an inequilibrium state. This is known as transition state. And the energy required to go through this state is known as the activation energy in this case. So to describe this this way, first Frank Levy tried to describe this one by using the Frank control rules. He says that first in the ground state position is going to the reorganized and make a excited ground state positions, and then is relaxed down to the product. But this theory cannot explain this in some reaction medium or solvent effect, and then it's modified by the Marcus, and he got a Nobel Prize for this theory in 1992. It's a very late after that. And he explained that we don't need to excite it to the ground excited state. Rather than is going to the saddle point, this is a cross section of the ground and excited potential curves, and then is relaxed down to the product. Product. So in this case, the energy difference, activation energy difference is much lower than the another theory, previous theory. So to explain this theory by using the MATLAB script, this is the methodology. I already skipped some equations, time equation here and other because you already seen that. So the coordination is changes in the reactant and product. So the wave function also changes, and we can say that the Hamiltonian also changes. The activation and excited state Hamiltonian and down state Hamiltonian, we can relate by this equation. It changes with the time, and the HGE and HEG is Hamiltonian for the electron coupling and is making 0. And the reorganization of the nuclear position is harmonic oscillator. So that's why this potential of the excited state electron potential and ground state potential are describing by harmonic oscillator equations. In this term, and this is giving us the curvature of this parabola, and this one is giving us the equilibrium energy on the ground and excited state. And the reorganization energy we can define by this equation. This one is the constant, and dP and QR is the equilibrium position of excited state and ground state. And if we know there is a reorganization energy, then we can define the activation energy by this equation from here. And it's also related with the energy change, enthalpy change of the reaction and product in this reaction. By using these all equations and MATLAB script, then to do that, first we need to parameterize the MATLAB script, initial conditions. Then that's why we just take aluminum and phosphorus doped silicon quantum dots, and then we optimize in the ground state and excited state in Bart's software, and then we took the energy. And the left side, I'm just illustrating the reaction procedure here. It is if after absorbing a photon, then electron is transferred from the N type to P types, and the next is the half reaction of this whole process. So to that, and this energy, this is the this energy getting from the calculation of the batch calculations. And if you see that I also taking the distance, atomic distance between the phosphorus and aluminium. And if you look on that, this change that in excited state and ground state, it changed by the 0.25 atomic units. Sorry, 0.25 in angstrom in average. So in excited state, in ground state difference is by moving the 0.25, and in atomic unit is a 0.5. That's why in my graph, in MATLAB script, I put the distance between the two excited state and ground state parabola is a 0.25, and plotted these two graphs. In here, this one is red one is indicating the ground state, another one is the excited state. So, and then after I run this script, is showing the time wave packet evolutions after that, and when it's crossing the settle point, is wave packet is accumulated in the excited state. This is indicating by the blue one in the blue graph. And then by the rate equation, I did not indicate in methodology the rate equation. How can you rate, because you already see that in the previous previous presentation. To do that, I change the initial momentum, which indicating the change of the temperature, and I will take the reading of this rate of the electron transfer. If you see that this it looks better than Pilan one. Actually, I did that. I didn't report the whole thing. All rate. I took only intermediate. Almost 200 degree Kelvin to 500 degree Kelvin intermediate. This giving us a more straight line. So then I plotted. I took the, if you take on the Arrhenius equations, and then I simplify this one. Then I plot this one long rate over 1/t graphs, and this giving us a straight line, and the slope of this graph is indicating this term activation energy over Boltzmann constant. If we calculate from this plot, we got the rate of that activation energy is 8.5 into 10 to the power minus 5 electron volt. This is a very small activation energy. And from the potential curve, I also calculate the activation energy. This one is a 0.8 Kelvin. This is a little bit much difference from this one. Calculated one and the plotted one. It's not a little bit, very huge difference. That's because of actually in this calculation we didn't consider the 0 point energy. Maybe that's why we make this, and this potential is much higher than the other one. And also I didn't consider the vibronic coupling. Maybe that's also contribute this energy. That's why in this calculation is giving us a very small activation energy. In the next plot, I'm just showing the some dynamics of with the time. This is showing how the probability with the change in time. As this activation energy is very small, the changing of the potential of these dynamics doesn't change huge. But this plot here, when the initial potential is 16 atomic units, and I saw that the rate of the electron transfer is highest in this potential. But if you see the dynamics is very hard to see in difference here in my computer, so there's little bit difference in here. And this one is when the initial momentum is 30. From everything, I just conclude this. My chart. First one is the Marcus theory is just another representation or based on the Arrhenius theory, Arrhenius equations, and the activation energy and potential differences in two methods is very much high because of we excluded the 0 point energy and vibronic coupling corrections, and the reaction coordinates also measuring the amount of the charge that are transferred. That means how much charge is change the reaction coordinates, and that also change the activation energy. And here on the solvent fluidity also have an effect on this one, coordinate. And dependent electrical energy is driving force with del G naught, reorganization free energy is from the just theory.
Okay, please join me in thanking